Diane Peters from Mechanical Engineering, and let me give you just a quick overview of ASCE. And then Reck from Mechanical Engineering, Girma Tewolde from Electrical and Computer Engineering, and Farnaz, Ghazi, Nezami, who can't be here today, but she has voiceover slides for the presentation that she gave at ASCE. If anyone is interested in joining ASCE, some of the benefits for membership are listed here. There's the Journal of Engineering Education is the premier educational scholarship journal. And there's also Prism, which is another magazine style that has been very valuable in bringing engineering education to evidence-based discipline. If you're not a member, there's applications here. If you're a first-time member, the Dean's program allows you to get the first year paid for by Kettle, or soon the Dean's office, and the second year by ASCE. So your first 2 years are free, so you can enjoy the benefits and make sure it's for you before you pay that $100 membership fee when you're a full member. The conference proceedings, I'm just highlighting 5. You should know that Diane had at least 4 every year. She gives multiple papers, as do many of our colleagues. So we just wanted to give you a highlight, 3 to 4 slides for each one of these 5 papers, so you get the gist of what ASCE paper would look like. Currently, there's 27 ASCE members at Kettering University. There have been more, and I strongly encourage you to get involved. So without further ado, let me turn this microphone over to Diane.
I appreciate everybody being here. It was kind of hard to actually decide which of the 4 papers would be most interesting to showcase because, of course, I did them because I thought they were all interesting. So if anybody wants to talk to me later about my others, I'd be happy to. But in the interest of time, I'm just going to focus on one, a survey of types of industry-academia collaboration. And this was a joint paper that I did with a friend and colleague of mine, Dr. Ann Lucietto, who's on the faculty at Purdue in engineering technology. So we know that there's a long history of industry-academia collaboration. It's been around for a long time, but there really isn't a lot of research on it, which in some ways is kind of surprising. We know that it's good, and we know it's effective, but it hasn't been extensively researched, which is why Dr. Lucietto and I decided we wanted to at least start some kind of an effort with this paper. A lot of what does exist in the way of research focuses on the impact on students rather than on faculty or industry, which are 2 important pieces that we really need to understand. Benefits to industry do include access to students, which they all need, and access to university resources, both physical and intellectual. That's kind of one of those motherhood and apple pie statements. Everybody knows it's true, even though we haven't extensively proven it. And there are some benefits to academia as well, and one of them is staying current with industry practices. That's where our students are going, so it's good for us to know what the needs are and what's going on out there. And it's a benefit to the students while they're here with us in academia because they learn some real-world engineering. And at Kettering, we know that quite well since our students do co-op. So we looked at some of the different types of collaborations out there to see what are the different models and what do they look like. What is out there in terms of either published papers, which there isn't much of, or in terms of websites for various different institutions. So there are a couple of different kinds of collaborations that exist. Some of them have multiple universities, and some of those have individual companies, and some of them have multiple companies. There's a number of different multi-university, multi-company ones that we highlighted in the paper. Just one example I would mention is the Automotive Research Center, which is headquartered out of the University of Michigan. It involves government as well, TARDEC. It involves a number of local automotive companies, and it involves a number of universities, including U of M, Wayne State, and a number of others. There's also some single university collaborations, and they can be with multiple companies, and a lot of times that's in the context of co-op programs, which we have, and which there are a number of other co-op schools. And sometimes they're individual companies. Some universities build very strong relationships with individual companies, and that's more akin to what we once had with GM when we were GMI. One of the big takeaways of this paper, and one of the things that I want to highlight about it, is that we didn't pretend we had all the answers. We did a survey of what information was out there, but one of the big purposes of writing this paper was not just to document what was out there, but to raise questions and raise awareness and try and launch some research efforts. So this paper is the start of something that Dr. Lucietto and I hope to continue. So I want to highlight some of the open questions here. One of them, of course, is what types of projects lend themselves well to collaboration. not everything is an equally good collaboration opportunity. What are the different approaches? And one of the things that did come up in a lot of this survey work was intellectual property and technology transfer. In academia, one of the things that we need to do is publish. One of the things that industry needs to do is protect their intellectual property, often through patents, but sometimes through trade secrets, in order to avoid doing a bunch of work, paying for it, and having someone else reap the benefits by just making it cheaper. Also, how or if universities with co-op programs leverage that is something that has not been extensively researched. How do we link up co-op programs with faculty research? It's done, and a lot of people can talk on kind of an anecdotal basis about what they've seen and what's happened, but nobody's actually done any kind of a survey or a study or anything to document how that is and how it works and what are the best practices, which would be a really important question. Another important question is, how is it different in the US from other countries? Some of the literature that's out there, in fact, a good part of it deals with other countries, and it is very different from one country to the next, in part because of the different regulatory environments and the different levels of involvement that governments have in different industries. It also varies within the United States. For example, here in Michigan, we're heavily into the automotive industry. Other areas have other prevalent industries. How do students benefit? We know they do, but how do we do that well, and what are all the ways? How do you get the projects to fit student capabilities? Because there's some things that would match better with students and some that really should be done by faculty because of the skill level required. And then, are the industry expectations really in line with the students' abilities? So those are really important questions, and those are a lot of things that don't have answers. So one of the outcomes of the paper, and one of the reasons we presented it, was to try and gain collaborators from various areas. And that is one of the benefits of presenting at ASEE, is the fact that you get to showcase your work to others, not just to show off what great stuff you've done, but also to build a community and find new collaborators. So that ends my presentation. I'd be happy to talk later with people if they want to, but in the interest of keeping us on time, I'm going to introduce my colleague Rebecca, who is going to be talking about a totally different kind of paper, which she's done in the past at ASEE.
Good afternoon. I am Dr. Rebecca Reck. I am in the mechanical engineering department, and in the interest of picking one of my papers that would be a broad applicability to the Kettering audience, I picked my paper from last year for two reasons. One, because I think it's a more interesting paper for the broader Kettering audience, and two, because it's not a typical conference paper, and I wanted to highlight the variety of papers and that you can submit to a conference at ASEE. So the acronym at the beginning of this, BYOE, is Bring Your Own Experiment, and it's a science fair style paper. And so part of my doctoral dissertation work, I designed an affordable and portable laboratory kit that I did a lot of research on to replace this extensive lab bench that you see in the picture. And this style paper, I actually brought the kit with me to Seattle, because this was a 2015 conference, and did a science fair style demo of the kit instead of a traditional paper presentation. So I wanted to show you what that looked like. So the Bring Your Own Experiment papers are part of the Division of Experimentation and Lab-Oriented Studies, which is one of the many divisions of ASEE that you can get involved in. It's a multidisciplinary division, so they take lab and experiment type things from all of the different engineering disciplines, which I find very fascinating to be able to learn from other disciplines when coming up with these, especially in controls, being a multidisciplinary field in of itself. Sometimes I find weird places as a home for my papers. The paper is in the form of a procedure and a description of the lab itself. It doesn't have some of the same traditional content. And the goal of the paper is to allow other people to actually copy your experiment and implement your experiment at their own universities. So it's a slightly different style paper and a different audience and goal. And then, like I said, you have this science fair style demo where we have tables around the outside room, and you just rotate through the tables on the same sort of schedule as a paper presentation, and you just demo your experiment for other folks. So some experiments in, say, chemistry or some of those might not travel very well. My kit, when you see a picture, I had some qualms about getting through airport security with it myself. So you got to keep that in mind. But hey, next year we're in Columbus, you can drive it there, so maybe that'll help. So speaking of my kit, this is a picture of the kit that I demoed with this type of paper. It replaced our Intro to Controls lab for the general engineering program at the University of Illinois. The lab bench that you saw on my first slide roughly costs about $15,000 per station. This one, on the other hand, costs about $130. So two orders of magnitude increase, and my research showed that educationally they are equivalent. The students achieve the same learning outcomes with the old equipment and with this kit as well, because we ran a quasi-study while I was still at Illinois, and half of the students used the old equipment and half of the students used this equipment. But that was not the focus of this particular paper. The focus and the outline of this particular paper was a little different, and because this is a different paper, I wanted to highlight the outline of my paper. So I started out with a summary of what I was trying to achieve with this kit, what types of experiments, what level of students it was aimed for, that sort of thing. I gave it some pedagogical context. Was the intent to be an in-person lab, something they could take home, what class it was for, what the objectives of the class were for, how many times a week they met, they used it, those sorts of things. Then I gave a list of the sample experiments that I had already completed with the kit and was able to do with the kit. And then the biggest section of this paper was the technical design. I went through, I had a bill of materials, I had circuit layouts, I had some of the assembly instructions, I had a link back to the website that included all of the full lab instructions that we used and various things like that. Then, just like any paper, I did have a limitations section, some of the things where we were still working out the kinks in the design, so folks were aware of some of the hurdles that they might need to they would come across. Then talked about the implementation, how we used it in the class, and from that perspective, then just like any paper, we've finished off with conclusions and future work. If you want more information about this, the Division of Experiment and Lab-Oriented Studies, DELOS for short, has a sample paper out there, and you can actually go look at mine on the website as well. And with that, I will turn it over to Girma, who is going to talk about the IME 100.
Hello, everyone. Thank you for coming. So my paper I'm going to talk about here is innovative course modules for introducing ECE to engineering freshmen. This is the renovation that we did in the IME 100 class. And for those who are not familiar with this course, this is an intro-level class given to all freshman engineering students. And it's focused only on the ECE component of this class. And the idea was this course has been running for quite some time, and there were, the materials were being outdated, and it did not give them, the students, opportunity to explore beyond what's given, in the actual assignments in the classroom. So we tried to put in some components that give them innovative creativity experience in the class. And there are 4 course modules that were created. And by the way, this course development was sponsored through the Keen internal grant, and it's been done through about a year development time. And we have those 4 course modules. The first one is briefly introducing the students to the electrical and computer engineering, the field of electrical and computer engineering, and the tools that students get to use in industry for building and designing electrical circuits. And in addition to that, in most of the course modules, as you see here in blue, the students get exposed to entrepreneurial mindset. So how do you explore beyond what's given in the classroom? And how do you actually make connections between the theory and the classroom concepts to real-world applications in the industry? So that's introduced in the first class, and then through a number of tutorials and extracurricular activities outside for them to do research and exploration. They address those issues. So in the first course module, they do that introduction to ECE and learning about the tools. Then in the second course module, they apply those techniques in building and constructing an actual circuit board based on the design that they have created in the first course, in the first module. Then in the third course module, we give them a different approach of designing an electrical or an embedded system type problem. And this is using a microcontroller. We use an Arduino microcontroller, which is an open source hardware platform which is being widely used in hobby-type projects, in classroom projects, and it's a low-cost, open source, and it's very easy for the students to get their hands on, and they can even buy their own parts. These are low-cost components that they could utilize. So in the project activity here, they do recreating the first project they did in the first course module, but this time using an Arduino-type microcontroller. And they can try to appreciate the value of doing it using an embedded processor as part of their system versus a pure hardware design using an actual electronic components. And things like flexibility and the adding new features, how easy it will be based on an embedded system type platform versus a circuit design using an actual hardware. They can appreciate that value. And then in the course module number 4, we introduce them to technologies in sensors, actuators, and motors by using a robotic platform. So they get to take the Arduino microcontroller and put it on a robotic kit. This is created in-house using the components that we purchased online. And they integrate motor controllers, ultrasonic sensors, and light sensors to build an autonomous robot. And by doing that, they learn programming techniques on how to incorporate control algorithms in the robot, and learning about sensor technologies. Beyond what they do in the robotics, they can even see how those sensors could be used in industrial type applications, for safety and automation in industry. And there are tutorials in all of these course modules that the students are encouraged to look up before they come to the classroom. That way we can make the most out of the limited class time we have. And and as you can see here, these were put online. So at the end of the first meeting, for example, the students are encouraged to go online and look up those tutorials before coming to the next classroom. So they get prepared to do the activities that follow up in the following week. And this slide shows pictures of some of the projects that they get to do in these course modules. The first one is a software tool we are using to teach the students on how to create a circuit design using an NI multi-sim software. So we use an example, a traffic light controller, so they can easily understand the process that goes on in implementing this type of system. The basic components, timers, counters, LEDs, and logic components. Those are basic elements that are utilized in many hardware implementations for different types of systems. So we introduce them many of these elements, and then they learn how to put them together to realize, in this case, a traffic light controller. So they create the design and build a simulation to see how this system works. They learn how to manipulate some of the components, such as a potentiometer, for example, in here, to see how that impacts the operation of the traffic light controller. So once they understand how the system works, the following week they actually build the circuit board. And then they learn the skills that it will take to assemble this type of board. The soldering skills are introduced, and we demo that to them at the beginning of class, and they apply that to actually construct the board. So they would be able to identify the different components, LEDs, resistors, potentiometers, and so on, and put them up together and do the testing using an oscilloscope, a multimeter. So they get to know all the tools that are needed to do this type of design and verifications. This is a screenshot of the actual simulation they carry out when they did the design, the circuit design. And that's a picture of the actual robotic platform that we put together using the different types of components. We built in-house the light sensor for line follower, and then mounted an ultrasonic sensor to make the robot autonomous. So it gives them a fun way to learn about different sensor technologies that could be applied in autonomous vehicles, in industrial safety, in all kinds of different applications. So the main focus is, after we cover these different components, we give them challenge to go out and explore. What else can you do with the concepts and the theory they learn here in the classroom, and find other, ways of adding features or finding products out, they use day to day in their own lives, and see, what type of components are they made of, and what type of additional features they can add to expand those functionalities. And we did a preliminary survey on how effective the course modules have been in the learning process of the students. In the actual paper, there is a actual list of questions for the survey. And we did pre and post measurements of the data. We collected the data before they took the class and then after they finished taking the class. And those numbers show us, how much improvement they have made in terms of learning the course material. And there were also written comments on how much, fun the students had, playing with the robots, and it turned out to be a fun experience for them. All right, so with that, I finished my part, and Terri could introduce the next speaker.
So our next speaker is virtual. So Farnaz, Ghazi, and Nezami worked with Masoud Tavakoli and Mo Torfe, and she sent some slides.
Hi everybody, thank you so very much for listening to my presentation. I'm sorry that I could not be there and present my paper, but there was a conflict with my schedule, and unfortunately I had to attend another meeting, and that's why I had to skip my presentation. So that's why we decided to record this presentation. In today's presentation, I am trying to provide a very short summary of my work, which is the result of my King grant that I did a while ago in one of my classes, which was the IME 452 course. And the name of this project was Developing Entrepreneurial Mindset in Industrial Engineering Classes. A case study is a paper that I presented in ASABLE 2016. And this paper was done in collaboration with Dr. Tavakoli and Dr. Torfe in Mechanical and Electrical Engineering departments. So the main objective of this King Grant project, or this paper, was to infuse entrepreneurial mindset and promoting the entrepreneurial-minded learning among undergraduate students. But the main challenge that we have had is that how can we restructure engineering courses while still not to significantly increase the students' workload, while still achieving the EML goals and using the King principles. Because we already know that our students are so busy, the course loads are already heavy, so we don't want to significantly students' workload, but still we want to infuse this type of mindset to our students. So the question is that how can we restructure these courses to add something new to this, to infuse a new concept into our courses. The IME 452 course, which is Designing Value in Supply Chain course, was chosen to implement this concept, and it was funded by And as a result of this grant, I developed 4 modules in my class. The very first module was an introductory module that I tried to explain for my students that what are the expectations for them. We always talk about the importance of EML learning. What is EML? What are the entrepreneurial mindset? What is the importance for the students? But we always target faculty. I was thinking it's very important for students to know why are they posing to these concepts, and what are their required skills that they should have in future. And this type of pre-knowledge will make the learning process more meaningful for them. So I prepared an introductory module for them, and I told them that why do they need to have this type of skills, and how each of upcoming modules will help them to develop these type of skills. And the rest of the modules that you see over here, module 2, 3, and 4, they are more technical modules which are related to the course material. The module 2 is a demand forecasting module where students were able to use some demand forecasting techniques to implement different techniques on their own wireless, minutes, and cellular data consumption in order to in order to predict how much data and minutes they are going to use, for example, next year, and as a result of that, which provider in the market is the best or is the most economic provider in the market for them. And after that, they have to do some supplier selection problems, some multi-criteria decision-making problem, which are some industrial engineering concepts. They have to implement different concepts to select the best provider in the market. And after that, they have to implement a course map module, which is that they have to. It was a project which was defined at the very beginning. It was defined at the very beginning of the course, and this project was completed as the course was evolved. It means that the students were supposed to define a new product or service to be released to the market. And then students have to, as the course evolved, they have to, for example, implement demand forecasting, see how much demand this product or service will have, what is the market for this product. They have to see how they can transfer customer needs and expectation into design features. So the students have to complete this project all the way to the production. So we have to stop the production at the production phase. So students need to use different techniques that they have learned throughout the course. And the very last module that we have in this course was energy management module, which was the part of their Lean project. Students need to learn how to come up with some energy saving recommendation on campus. For example, they had to literally walk on campus and see where there are some areas that they see energy consumption, and they see areas of energy waste on campus, and how they can do some feasibility assessment in order to come up with some recommendation. And once they come up with recommendation for one of their solution, they have to do the analysis in order to come up with dollar values in terms of how much energy they can save and what is the cost of implementation, and doing some economic analysis. So as a result, as you can see in all these modules, they have to implement, they have to apply different skills, and they have to really work on real life problems. So in order to collect a student's feedback, I was able to collect some students' feedback, and as a result of this students' feedback, generally I found that these modules were very positive, had a very positive impact to promote students, to promote the entrepreneurial mindset among our students. And also, since all these activities were performed in a group, it helps the students to enhance their teamwork and leadership skills, and also from the pedagogical aspect, it helps students to improve their active learning, and also students were able to actually implement multidisciplinary skills, multidisciplinary tools in order to solve one real-life problem. And using these modules, the students were able to integrate a mix of industrial engineering tools to solve real-life problems and practice different course concepts with the goal of creating value for society, for their customers. And as I said, there is no based on my standardized data, there was no statistically significant difference between a student's performance in different modules. That's the end of my presentation. I don't want to take more time. I would like to thank you all, and I'm sorry that I'm not there to take your questions. Thank you.
And then I had a couple of papers this year, and they were in the Industrial Engineering Division. This is one of them. We had an experiment looking at office ergonomics. We did it within the ergonomics classroom. And just out of curiosity of the people in the room, how many of you do heavy lifting as part of your job every day? Not so much. How many of you use computers for a good portion of your day. Okay, so that's pretty typical. In past history of ergonomics, there was a lot of heavy lifting, but if you see from this picture, what we have down in the ergonomics lab is a walk station where you can use your computer, adjust the height of the desktop, and move your body while you're working. So the idea of having some amount of body movement, I really thought would improve productivity. And the reason that this is important in the industrial engineering classroom, particularly in ergonomics, is that we know we're sitting more. And if we want our workers, if we're designing the workplace to be a place where people are healthy and productive, we have to worry about the seated posture that we're in, rather than in the past, how to lift heavy boxes, how do we sit for long periods of time without cumulative trauma disorders. So we designed this experiment in the ergonomics laboratory where we were comparing that stand-up walking workstation to a typical stand-up workstation to the typical cubicle, sit down and sit in one place for the entire time. And what the students did is they gathered data. They were actually the subjects in the experiment, as they are every week in the ergonomics lab. But we were looking at different computer tasks. And we were using this index of difficulty based on Fitz tapping task, where the more difficult the task, the more slowly you can move the computer mouse back and forth. So along the x-axis here, the index of difficulty says the index of difficulty is increasing, and it gets harder as the target gets smaller and as two targets get farther away from each other. So what this clearly shows is as the index of difficulty increases, the time to complete the task also increases. And students took the data and they had to use their prerequisite course in statistics to see if that was significant for difficulty in 3 different postures. So we were looking at walking, sitting, and standing. I really thought walking would be more productive, and it turns out in every case, walking makes a slower task. So if you're trying to walk and use the computer mouse at the same time, it's not as productive, it's actually slower. So we can extend this into a research field and say, how do we, there is some element of productivity that will help us, but in this quick task, walking was significantly slower. Sitting, it turns out, was the best for very simple tasks, and as the task got more complex, standing was a better alternative. And the students looked at that through statistics. The relationship between movement time, time to complete this task, index of difficulty, and the 3 different postures that you might be in a typical workday. So as is required in an ASEE paper, you have to show the educational impact. So in this class, we did a pre-test, post-test, like Girma did as well. According to the syllabus topics, in every case, they learned something, so that makes me feel like I'm doing my job. But there were specific topics related to this experiment around Fitts law was one of the topics that they had the least information about, and computer input efficiency were the specific topics that we were looking at for this task. So here's the call to action. That's just a sampling of the papers that you might find if you go to the ASEE conference. So what's next? Next year in 2017, the conference is in Columbus, Ohio. So that means we can take a van of Kettering faculty and we can share rooms and we can get more people there, in economies of scale will let us do it less expensively. If you think you might be interested, I would strongly suggest that you put in a paper. So the abstracts are due September the 6th. It's a 3 review process. I'm sorry, that's when they open. October 16th is when they do. You can't submit until September the 6th. So the cycle is an annual cycle of submit an abstract. Once it's accepted, then the draft paper is usually due right around Christmas time, and then the final paper is due in the late March time period. So these dates are all available on the website. You don't have to write it all down. But it's an annual cycle with a very critical review with like-minded peers. So I've had papers rejected in ASEE, I'm embarrassed to say, but they do a nice review. Every paper that I've submitted and that has been reviewed ends up better because of the review process by colleagues who are in a similar area that I'm in. So some of the things we wanted to talk about were how to come up with funds. I want to mention that if you have never been an ASEE member, the Dean's program allows you 2 years for free. The first year is paid by Kettle, or soon to be the Dean's office, and the second year is paid by ASEE for new members. If you've been a member in the past, you can re-up your membership. We've got applications down here for you to join. There are a number, probably 30 different divisions that you might be interested in, including a library division, a liberal studies division, and educational research and methods division, where you can find other educators, not just in engineering, but who teach students like we typically have here at Kettering. We wanted to talk a little bit about if we could get a critical mass about coordinating the university. Some of the bigger schools, like the Rose-Hulmans, they all wear the same color shirt, so it gives some name recognition to the school. I've been contacted the last couple of years to do a video about the school. That's rather expensive, and so far we haven't allocated those funds, but it gives Kettering a name recognition in the field of engineering education that you can't find somewhere else. So this society has a lot of impact for the university. We will be having a Tuesday teaching talk in the first Tuesday in October. So thank you for those ideas. I know Rebecca and Diane have been extremely active in ASEE all along. And Girma, Farnaz, a lot of the other, go through all the list of ASEE members here, are trying to become more active. So we'll have an abstract development discussion on October the 4th in Kettle to make sure, if you're just thinking about putting a paper in about what you're doing in the classroom, to have peers look at that abstract and give you some ideas on what would make it be accepted. And honestly, some of the papers that were not accepted didn't have an educational impact. If it's research, research is great and it's likely in your technical discipline, but you have to show the educational impact if you want to include it as an ASEE paper. All right, if you want to look at previous papers, asee.org is their website, and Rebecca brought to your attention already peer.asee.org. You can look at some of the past papers. You can search by author and by topic.